Hi there, folks. Today we're looking at linear, quadratic, and exponential models. The fact of the matter is we've already learned how to graph all of these things. Now it's just a matter of just quickly identifying what kind of function am I dealing with. And there's a couple ways we'll identify that. We'll identify it based on the equation. We'll identify it based on the graph. We'll identify it based on the situation. All right. So just a quick refresher. The most basic and most universally used version of a line of a linear equation is y equals mx plus b. Remember, that's where b was the y-intercept, and then m is kind of like the slope, and we would count up and over to create this line. And hopefully we all remember that. Quadratics, we just did those not too long ago. But quadratics, remember, you have to have a vertex for these, and that's where you do opposite of b over 2a to get the x value, and then plug it back in to get the y value. And remember, these are u-shapes, so we find the vertex, and then we use the a value to kind of get the appropriate shape of this thing, and then draw our parabola, our u-shape, all right? And then exponential models, this one is probably the one that we remember the least, but remember the a value is kind of like our y-intercept, and then the b value is like what we're multiplying by. So if it was a 2, we'd be do times 2 divided by 2 going the other way. Remember, these are the ones that get closer and closer to the x-axis but never touch it. They hug that line, and they just either increase or they decrease if they're exponential decay. But these are the couple things that we've graphed this year. We've also dealt with absolute value functions, but they kind of fall under the linear category. But again, it's about quickly recognizing these things. So based on the graph, we should be able to quickly recognize them. And then based on the equation, we should be able to quickly recognize. So like if it's in the format for a line, or if it's in the format for a quadratic, or it's in the format for exponential. Here's the giveaways for these. When you look at a linear function, the biggest x value is an x to the first right here, and that's the giveaway for a linear function. It's all about that biggest value being x to the first. The quadratic, the biggest value is an x to the second. That's the giveaway for the quadratic, all right? Don't get hung up on, oh, well, it's missing the bx term. Well, it could be that b is a 0, all right? It could be c is a 0, that kind of thing. Exponential, the big giveaway is look at where the variable is. The variable is the exponent, okay? And that's a big difference. That's a departure from some of the rest of these things. So again, look for those kind of key pieces. Biggest term being of x to the first is linear. Biggest term being an x to the second quadratic. If the exponent is the variable, then it's exponential. For example, if I look at these guys, so like this first one, it looks almost like y equals mx plus b, but the problem is instead of an x to the first, it's an x to the second. Since the largest x term is an x to the second, that's the giveaway for this thing being a quadratic. And I'll just abbreviate. Okay, but you'll notice it's missing the bx term. Well, that just means that the b value is 0. That doesn't mean that it doesn't exist or it's not actually there. It's just that when we have 0, we don't actually write it. Okay, this one we see the variable is an exponent, so that's the giveaway for this thing being an exponential function. This one, it fits the y equals mx plus b format to a t. We've got an x to the first as my biggest value, so this one is linear. This one, it looks kind of like the exponential format, but it almost appears as if a is missing. But again, it's one of those tricks of math. We know that there's a 1 out front. Now it's in the format y equals a times b to the x. But again, the key is that the variable is the exponent. So this one's exponential. This guy, y equals mx plus b is the format here, but we can't see the m value because it's a 1. We can't see the b value because it's a 0, but it's still that format. Again, the giveaway is the fact that the largest x term is x to the first, and that's what makes this thing linear. And see, it's important to be able to identify these right away so you know what approach you're going to take for graphing. And then this one, the biggest x term is an x to the second, so this one's quadratic. So again, it's just quick recognition. I need to know what kind of function this is because that dictates my approach for graphing. It dictates my approach for solving all kinds of stuff, okay? So if I look at these guys, again, I'm jumping around a little bit. I'm going to plot each of these points and then just kind of look at the function. So now we're identifying this based on the graph. So here I've got 1, 3, 0, 0. -3, 3, kind of looks like gibberish at the moment. -1, -1, and then -2, 0. And so as we look at this thing, hopefully you recognize that that's not a V. It's got to be a U shape. It's got to be a curve. So this one has to be a quadratic because of the shape of the graph. If I look at this guy, again, I start plotting these points. So 0, 2, -1, 4, 1, 1, 2.5 is right here. And as we look at this thing, it looked almost like it was going to be linear for a second, but now it's starting to gradually slow down that kind of descent, which means this is a curve. It looks like an exponential model. And there it is. Okay, so this one's exponential. So again, start looking at the graph and determine, okay, based on the shape, what kind of function is this? And then this one, let's see, -1, -2, 0, -1, 1, 0, and let's see, 3, 2. It's right here. And we can see that the pattern that's being formed by the graph is a line, so this one's a linear function. But again, we want to identify it based on the equation. We want to be able to identify it very quickly based on the graph, okay? It's just that recognition of this is the type of function I'm dealing with, okay? So if we take a look at these next couple, we're going to identify using the difference, ratio, or second difference. And two of these we're already familiar with. Using the common differences for linear functions. Remember, when we look at a table of values, we determine if it's a linear function based on the fact is the pattern to get from one y value to the next y value the same every time? Are we adding the same thing each time? And then exponential, when we did exponential functions, we looked at the common ratio. We said, okay, is the pattern that we're multiplying by the same thing each time? That's how we know that it's exponential. The quadratic is the one that's much different than the rest, but really it's the second common difference. And a nice way to kind of state that is to say the difference of the differences. So we approach it the same way we do linear. We look at the common difference. We look at the difference between x and y. What are we adding each time? And if that's not the same, we just try again. We take the values we just wrote down. We take the values that we were adding each time to get from one value to the next. And we say, okay, how do I get from this adding value to the next adding value? Okay, it's the difference of the difference. And that one's a lot easier in practice than it is when we try to put it into words, okay? And you may notice something here. If we talk about linear, it's the common difference. So the first time we look at the common difference, the first time we look at what are we adding each time, it makes it linear. If the second time the common difference is the same, then it's quadratic. What would happen if the third time the difference is the same? Well, then it would be a cubic function. If the fourth difference was the same, it would be a quartic function, quintic function, and so on and so forth. So however many times it takes to find a common difference, that's the degree of the function, and that's what we're going to find out here. For example, if I look at this guy, again, I'm just trying to identify patterns here. And so I might try checking something like multiplication first and say, okay, to get from 4 to 2, I multiply by 1/2. And you don't have to write that down because I'm going to be wrong. And then to get from 2 to 0, I have to multiply by 0. And then here I have to multiply by, there's not really anything I would multiply, so it kind of putters out, and that one doesn't work, okay? So then I try again. I say, okay, maybe it's a common difference. So I look at the difference from here to here. I would subtract 2, so I go down 2. And then from here to here, I also subtract 2, so I go down 2. And here I subtract 2, so I go down. I subtract 2, so I go down 2. This is the makings of a linear function. Okay, the fact that the pattern is I'm adding the same thing each time, which is a -2, makes this a linear function. And we can even write the equation of that linear function. That's a terrible looking A. Let me try again. The equation of that linear function, y equals mx plus b, remember, this is the slope. That's what's being described here. So you could even write the equation of this and say y equals a -2x plus 0, because that's the y-intercept, okay? Not that the question asked for that, but we should be able to do that based on the fact that it's linear, okay? We've done linear functions before, okay? If I look at this one, same kind of thing. I look at the pattern, and maybe I look here and say, okay, to get from here to here, I subtract 2. and then I subtract 6, and then from here to here, it looks like I subtract 18. All right, so it's not the same, but the second common difference might be the same, so I have to keep going. So now I find the difference of the differences. So I go from -2 to -6 is down 4. From here to here, it's down down 12. So it's a -12. And those still aren't the same. See, if this first column was the same, it would be linear. If the second column was the same, it would be quadratic. All right. And I could keep going to see if it's a third degree or fourth degree function, but we're not dealing with those, so it's probably not going to be one of those. So the other pattern I check is multiplication. I say, okay, to get from here to here, I multiply by 3. And then here to here, multiply by 3. Here, times 3. So this one is exponential because the pattern is I'm multiplying by the same thing each time. And again, you could write this exponential function. You know that it's y equals -1 times 3 to the x. Remember, the a value is kind of like our y-intercept here. And then the b value is the thing we're multiplying by. Again, it didn't ask for that, so you don't have to have that written down, but could I ask you for that on something like a test or a quiz? Well, of course I could, because we already know how to do that. That's review. If I look at something like this guy, again, I might look for multiplication first, or I might look for the common difference first. Most of the time, students look for a common difference first, and then go to the second common difference, and then try multiplication. I didn't do it in that order for the first one because I didn't want to get the answer right away, because that would have been boring. But here, if I did the common difference, it's down 3, and then here that's down 1, and then here that's up 1. So obviously those are not the same. Let's check the second difference. To get from here to here, that's up 2. And then to get from here to here, that's also up 2. And so we can see the second common difference is the same, which means this is a second degree function, so it's a quadratic. And for this particular quadratic, you could figure out the value here, because you could just think about the graph, but you can see this thing is symmetrical right here. See, this end is going to be symmetrical to this end. You know what the next y value is. It's 4. So this is my vertex. And then from there, you could look at the pattern of the values and determine the a value. And we've done a couple questions like that. All right, I'm not going to go into great detail here, but this one would end up being y equals, this is our standard shape. This would just be y equals x squared. This would be the really basic one. Again, I'm not asking for that here, but that's something I could ask you for in the future. If I look at something like this guy, I might try to do like the difference here and say, okay, to get from there to there, that's up 1.5. Here, that's up 2.5. Here, that's up 3.5. And here, that's up 4.5. And really, with something like this, you might look at this and go, oh, this is obviously going to be multiplication, right? And maybe you would have tried this instead and said, hey, to get from here to here, it's times 4. But then to get from here to here, guess what? It's not times 4 anymore, is it? Okay, it's times, well, 1.5. Sorry, not 1.5. Oh my goodness. It's times 2 and a quarter, 2.25. All right. So this is not working out. All right. So now here I look for the second common difference. Here we go. This one didn't work out, so I go here and say, oh, that's up 1. That's up 1. That's up 1. The common difference is 1, and it's a second common difference, so that means it's a second degree, so this is a quadratic. Okay, so again, it's just about the pattern recognition, kind of going after that thing. Now this one's a little bit more difficult. What you would have to do if you wanted to write the equation for this, you'd have to continue that pattern. So like as you kind of continue the pattern going this way from the second difference, so you'd have to go down 1, so this would have to be a 0.5. So then look at the difference here and say, okay, this would have to be a 0 then. Okay, and you could work your way backwards and apply the same approach where you could find the vertex. So once you found where the pattern repeats, so find the vertex and then use that to determine the a value. But again, hopefully you can see how we could keep that going. Like the next one would have to be a -0.5 in order to make this still a 1, which means this guy, the difference here, has to be down 0.5. There it is, -0.5. So now I can see the vertex is right here at 0, 0. And I can see it's over 1 up a half. This one's actually going to be a y equals 1/2. x squared. Okay. And again, that's going through that very quickly. We've done that in more detail in previous lessons. Okay. So just be aware that that exists, that we can do that. And the reason we can do that is because we've identified this thing as a quadratic and we already know how to deal with quadratics. And that's kind of the gist of this lesson. All right. It's just a quick evaluation of what kind of function is this. So now I know what approach I need to take in order to find certain things, in order to solve for this thing, in order to find the equation, that kind of stuff. Okay?